This video is about logic gates. There are two types of electronic circuits. First, you have your analog circuits that output voltages and currents with varying values. Then you have your digital circuits that output voltages within a limited set of values. Most commonly, digital signals will be one of two values, either 1 or 0, or it could be considered low, where the voltage would be something like 0 volts, or high, where the voltage would be something like 5 volts. If you were to graph the varying voltages of the analog circuit versus the digital circuit, we will see graphs that look like these. The analog circuit has varying values of voltages ranging anywhere between negative 120 volts through to 0 volts to positive 120 volts, whereas the digital circuit has either an output voltage of 0 volts or 5 volts. There are no in-between values for the voltage. This is the basis on which logic gates work. Logic gates perform basic logical operations. They open or give a high output voltage depending on the combination of their input values, or they close and give a low output voltage depending on the combination of their input values. Various combinations of basic logical operations give rise to a complex circuit. The result of the operation is given in a truth table. So these are your 5 basic logical operations that you need to recall for CSEC Physics. There's your AND gate, your OR gate, your NOT gate, your NAND gate, and your NOR gate. So the truth table shows the output for all possible combinations of input. Let's examine the possible combinations for a logic gate with only one input. With one input, this is the input here, with one input and 2 possibilities, the values can either be 0 or 1. If we had 2 inputs, such as in this example, when input A is 0, input B can either be 0 or 1. So we will have 2 entries in the truth table to show this. When A is 0, B can either be 0 or 1. Similarly, when A is 1, B can either be 0 or 1. Filling out the truth table with these scenarios will exhaust all possible combinations. The maximum number of combinations is given by the formula 2 to the power n, where n is the number of inputs. So in the case where we have 3 inputs, the maximum number of combinations is 2 to the power 3, which is 8. We will show all 8 combinations by first taking one input, for instance A, and showing that half of the total 8 possible combinations has to be the case where the value is 0. So the first half is the case where the value is 0, and the last half is where the value is 1. Then for this first half, where the value is 0, we show that for the second input B, the first half is for the case where the second input is 0, and the second half is for the case where the second input is 1. And then we repeat this for the second half down here, where B is 0 and B is 1. Then we just keep on repeating it, taking it in halves. So C is the case where, this is the case where C is 0 or 1, 0 or 1, 0 or 1. And in doing it this way, we would exhaust all the possible combinations. Now let's look at the truth tables for the various basic gates. This is our AND gate. The AND gate says that the output is 1 if input A is 1 and input B is 1. So that is this scenario here. A is 1 and B is 1, so the output is 1. For all the other scenarios, these would produce 0 because both A and B are not 1. This is the OR gate. The OR gate produces an output of 1 if A is 1 or B is 1. So an output of 1 would be produced in this scenario here because B is 1. In this scenario here because A is 1, and in this scenario here because both of them are 1. We just want to know if any one of them is 1, and it would produce an output of 0 here. Let's move on to the NOT gate. The NOT gate takes whatever input it has and inverts it. So if you invert 0, what you get is 1, and if you invert 1, what you get is 0. Now this is the NAND gate. The NAND gate is like a combination of two gates. It's a combination of the NOT gate and the AND gate. So what you're doing is you are inverting the AND of the inputs. The AND gate says that the output is 1 if input A is 1 and input B is 1. So this would produce a 1 if it was an AND gate. But since it's a NAND gate, we have to invert the 1 and we will get 0 if we invert 1.
The AND gate produces 0 for these values.
If we invert 0, we get 1. So this would be your truth table for the NAND gate. This is your NOR gate, and it is similar to the NAND gate in that it is a combination of the NOT gate and the OR gate. It says to take the OR and invert it. So what we're going to do is take the OR of the inputs and then invert it. The OR gate says that the output is 1 if A is 1 or B is 1. So the OR gate produces 1 for these last three scenarios. If we were to invert 1, we get 0. So the OR gate produces a 0 for those scenarios, and it produces a 1 for this scenario. Now here are two examples. It says to complete the truth table for the following combination gates. In this example, we have two gates. We have two AND gates. The first gate takes input A and B and outputs it as AB. Well, I am calling it AB for this example. And the output AB combines with the input C to another AND gate to produce the final output. So in order for us to get the final output, we have to deduce what is AB. AB would be the AND of inputs A and B. And we know now that we would only get a 1 if both A and B is 1. So we produce a 1 here, and we produce a 1 there, and everything else is 0. So the output now combines C and AB. And since it's an AND gate, you would only get 1 where both values are 1. So this is the only scenario where you would get 1. Everything else would be 0. And this is how you complete the truth table for this gate. Here's another example. This example uses a NOT gate, an AND gate, and an OR gate. It takes the output of the NOT and combines it with the output of the and use them as inputs for the OR. So let's do it in stages and find what is the output at D. The output at D invert the values at A. So D would be 1. This would be 0. E is the AND of B and C. So the AND only produces 1 when both inputs are 1. So that's these two scenarios. Everything else would be 0. Now the output is the OR of D and E, since D goes in here. So if it's OR, you would produce 1 if either D or E is 1. So we produce 1 here, 1 here. This would produce 0, 0, 0. And that is how you would complete this truth table. And that is where we will wrap up this video.